This semester we used a feedback control system to create an upright robot. An upright robot is a relatively lightweight, two-wheeled cart that is able to stand upright despite gravitational forces and other disturbances. The wheels can be coupled so that the upright robot moves in one dimension only. The upright robot requires use of digital control due to the sensors that need to be used, a gyroscope, and an accelerometer. The self-balancing robot is similar to an inverted pendulum. It balances better if the center of mass is higher up on the body relative to the wheel axis. The motors we chose were UXL DC 6V 300 RPM micro speed reduction motors. They run off of battery supply. When supplied with a DC current, the motor should be strong enough for the robot to correct its movements as needed. We picked wheels that perfectly aligned with the motor shaft. For the motor driver, we wanted a digital solution using PWM and a microcontroller. Since the use of an H-bridge was recommended to us, we chose the L298N motor drive controller board module. It is equipped with two H-bridge circuits. The module has two screw terminal blocks for each motor. We're able to control the speed by controlling and reading incoming PWM. For the PWM input, we need to pair the module with the Arduino Uno, a microcontroller equipped with 14 input-output pins, with 6 having PWM capabilities. For the sensor, we chose the MPU 6050 because it contains both an accelerometer and gyroscope chip. Reading values that come in is fairly simple, making fine-tuning one of the most important aspects.
For the body of the cart, we used AutoCAD to design a rectangular body. The body has a height of 6.5 inches, a width of 4 inches, and a thickness of 2 inches. As you can see, we have two smaller rectangular housings for the motors at the lower end of the body. The body also has two rectangular cutouts which create shelves to support the components. The hollowness of the robot promotes a more lightweight design without sacrificing the sturdiness. We also wanted to raise the center of mass to slow down the pivoting of the robot. The circle cutouts in each level of the body provide easier connections as the wires can be threaded through. Once we had finalized the robot body drawing in AutoCAD, we utilized the material extrusion 3D printers in Driftmeyer to print out the finalized design. We used 15% infill, rafts, and supports. After 10 long hours of printing, the body was finally complete. At this stage, we were ready to begin assembling the final robot.
Our overall circuit depends on a breadboard that the sensor is connected to. The battery runs the Arduino, which powers both the sensor and motor driver. Based on readings from the sensor, the Arduino code then reacts to drive the wheels where they need to go. When tuning the controller values, we tried to see how the robot moved and adjusted, but unfortunately, it did not agree with us. We decided to place the breadboard on the side because it was too large to go anywhere else. From there, we followed the circuit down to the wheels to create our balanced upright robot. Unfortunately, we could not get our robot to stand upright for any duration of time due to software issues.